In this video, we're going to talk about Hooke's law, which is the force that a spring applies to an object. So I have a spring, my slinky here, and what Hooke's law tells us about is if I stretch the slinky, the force that the slinky applies to my hand, or to both of my hands really, just like the tension force, the force of a spring, points in equal and opposite directions on its two ends. So as I stretch the slinky, the force on my right hand here points to my left or your right, and the force on my left hand here points to my right or your left. So these two forces are equal and opposite. And Hooke's law describes that force. So the statement of Hooke's law is that the force of a spring is equal to the negative of k times x. And so what we're going to do to start out with is we're just going to go through each component of that equation and think about what it means and try to talk about it in a logical way. Okay, so first, let's talk about k. So k is the spring constant, and it tells us about how stiff the spring is. So a more stiff spring means that it has a higher spring constant, k, right? So this spring constant we can think of as the spring stiffness. All right, so the spring constant of my slinky is quite low. My slinky is very malleable, right? It's not very difficult to stretch it, so it has a low spring constant. For example, the spring on a car, so cars have springs to stop them from, to make the ride smoother. And if you look at those springs, they're very thick and they're very difficult to compress or stretch. So those would have a very high spring constant. In general, the spring constant is unique to a single spring and it never changes for a spring. So this slinky has a given spring constant. The spring constant value, say it's 1 Newton per meter. That's the units of spring constant, which we will get to in a minute. If this slinky has a spring constant of 1 Newton per meter, it always, in all situations, has a spring constant of 1 Newton per meter. This does not change unless you change the spring. So I'd have to get a different spring if I wanted a different spring constant. Okay, so because force is directly proportional to k, we expect that a higher spring constant for the same x, which we'll get to, will lead to a larger force, right? So higher spring constant leads to a larger force with all other things being the same. Okay, so now let's think about x. So x is my vector that points from the equilibrium position to the object of interest. And it tells us how far the spring has been stretched. So for this, we're going to look at this diagram here. This diagram shows me my equilibrium position. So the equilibrium position is the unstretched and uncompressed position of the spring. So for example, this is the equilibrium position of my slinky. Now you could say, but it looks compressed, right? It's completely on top of each other. But this spring is designed such that its equilibrium position is fully compressed. So the slinky is not compressible. No matter what I do, I can't compress the slinky anymore. So this spring is not designed to be compressed at all. So it would just be its unstretched position here, right? And then x vector points from the equilibrium position to where the object that I'm interested in is actually located, right? So imagine that I have my hand is my box here, and my other hand my left hand here is a wall. So we're not going to worry about the force on the wall. The spring definitely applies a force to the wall, but we're not worrying about what happens to the wall, right? It's just going to stay there. So here's my equilibrium position. My spring is completely unstretched, and then I stretch it by some distance, x, right? So how far my spring has been stretched is given by this x vector. Okay, notice that, of course, force is a vector, right? And it equals a scalar multiplied by another vector with a minus sign out front. The minus sign tells us the direction of the force. So, if x points to the right, the force points in the opposite direction of that, which is to the left. So my force always points in the opposite direction of my displacement, x, right? So this is important. The force always points in the opposite direction of my displacement. If I erase here, I could think about a situation where I have the same object, but instead my equilibrium position is still my dotted line. Instead of being stretched, my object is, or my spring is compressed, right? So my x vector points from the equilibrium position to the location of my object. So this is my x vector. And my force vector points back toward equilibrium position. So x always points from equilibrium position to the object, and the force always points back toward the equilibrium position. And this makes sense even if I think about my spring, right? As I stretch the spring outward, my displacement vector, so let's just pay attention to my right hand here. As I stretch the spring, my displacement vector is pointing away from equilibrium. Remember, this is equilibrium position. My displacement vector is pointing away, and my force wants to bring the spring back, right? So if I let go, the spring would snap back to its equilibrium position, so my force points back toward equilibrium position. This is what the minus sign means, right? So just to review, our spring constant K tells us about how stiff the spring is. Our x vector points from our neutral equilibrium position to our object of interest's location, so our mass here. And the minus sign indicates that the force and the displacement vector x are always pointing in opposite directions. Another thing to note here is that the fact that the force depends on the displacement means that if I stretch the spring further, it takes more force. So I can stretch the spring just a little bit with only a small amount of force, and then it takes more force for every bit that I want to stretch the spring, right? So moving the spring from equilibrium position to 1 centimeter is easier than moving it from 1 centimeter stretched to 2 centimeters. It's easier than moving it from 2 to 3, etc., right? So the further it is stretched, the more difficult it is to stretch it more, right? That's what this dependence on x is, right? So this is different than other forces that we've looked at because the force is not constant. That is to say that as I stretch the spring, my force required to continue to stretch the spring becomes greater and greater as the spring becomes more stretched. So this makes it somewhat unique in the forces that we've looked at so far. Now let's look a little more closely at the spring constant and its units and what it means. So the units of the spring constant must be newtons per meter, because if you solve this equation for K, right? You ignore the minus sign when you're just looking at units. If you solve this for k, it looks like a force divided by a position, a force divided by a, well, distance. Force divided by distance, right? So your spring constant has units of newtons per meter. So as just kind of a visual example of this, imagine that I have a spring with a spring constant of 2 newtons per meter. That means that if I stretch the spring 1 meter, that the spring applies a 2 Newton force back on me, right? Because force would equal 2 newtons per meter, and I'll just do a magnitude here, multiplied by 1 meter is 2 newtons. So the magnitude of my force is going to be 2 newtons here, and I know that my displacement vector points from my equilibrium position to my object, which means that my force points back, right? And I could set up, for example, if I did a coordinate system where to the right is positive, then my x vector would be positive, pointing in the positive direction, and my force vector would then be negative, pointing in the negative direction, right? So if I do this, I can actually set it up right now. So if this is my positive direction and this is my negative direction, then my actual force in this situation, my force vector looks like negative 2 newtons per meter. That's my spring constant multiplied by 1 meter. And I will make this I hat, right? Because this is my x direction. So this is my force. My delta x is 1 meter I hat, my scalar here. And so my force vector is negative 2 newtons I hat, telling me that it points to the left here. Likewise, if I had the spring stretched for 4 meters, well then my force looks like negative 2 newtons per meter multiplied by 4 meters. Again, I hat, which is going to be negative 8 newtons I hat. So my force points back to the left with a magnitude of 8 newtons, right? So moving 1 meter is 2 newtons, 2 meters would be 4 newtons, etc. 4 meters is 8 newtons of force that the spring is applying to my box at that displacement. To see how we can deal with a non-constant force, let's think about graphing a constant force acting on an object. So what we're going to do is we are going to make a graph of the force applied to an object, and that is the force in the direction of the displacement, the force that I actually care about, which I will call F parallel or F cosine theta, right? This is the component of my arbitrary force vector that points in the direction of my displacement, and then I will graph my position x. So for example, if I have some box and I have a force which points this way, say it makes a 60-degree angle with the horizontal, my box moves to the right, so my displacement vector points to the right. Let's say that my box moves 5 meters and that it experiences a 10 Newton force up this way. So I'm only worrying about the work done by this force here, right? You can imagine it's on a frictionless table and that the normal force is acting on it and gravity is acting on it. And we could worry about each force and the work done by each force individually, but here we're just going to focus on this 1 10 Newton force. So the 10 times the cosine of 60 is 5 newtons, which means that the component of this force that actually points parallel to the displacement is going to be 5 newtons. So we can have a 5 Newton force. It is a constant force that is applied continuously for 5 meters. And what you should notice is that this area here is equal to my force multiplied by my distance, or my force parallel to my displacement multiplied by my displacement. So this area is equal to the work done by this force. And this works for any force that you're interested in, right? As long as you can find the component of that force that points in the direction that you are moving, and even if it points against the direction that you're moving, all that would happen would be that your force, instead of being a positive force, would be a negative force, and your area would be negative, leading to negative work, right? So as long as you have a constant force, you get a nice box, and you simply multiply your force by your displacement, and that area tells you the work that was done by that force. Now let's take this same idea of graphing the force versus displacement in order to find the work done by the spring force. So we're going to take our positive direction here to be in the direction of motion. So my graph, my displacement is increasing in the positive direction here. And then what I'm going to do is I'm going to graph negative kx. So this looks like a linear function. That is, my force looks like a linear equation for x. So I should get a line. That line should have a negative slope, right? So moving in the positive direction should give me a negative force, right? And it's going to have a slope of k, because this is where my x component gets multiplied by my slope to find the slope of the line. So here, let's imagine that I have some k value, and that this is my force, right? And let's imagine that I exert that force over the course of 5 meters. And let's imagine that my k value is 0.5 newtons per meter. Okay, well, in this case, the slope of my line is negative 0.5. So in 5 meters, I'll go 1, 2, and then a half. So this will be negative 2.5 newtons is where this line is. Sorry, try to fix this. Yeah. So my two lines should meet here, my force line and my y component line here should meet. And now I'm interested in the area between my force curve and the x-axis. This is always the area that I'm looking for. Okay, so that means that this area here must be the work done by the spring, because it is the area between the force of the spring and its displacement. So this is the work done by the spring. Okay, so let's call 5 meters here for the moment. We'll call it x max is my 5 meter displacement. So if we want to find the work, we need to find the area of this blue shaded region. And the way that I'm going to think about doing that is I'm going to take this full box that I've drawn and note that the area must be half of that full box, right? So I have a box where this is my line and this is what I'm interested in. One side of this box has a length of, and I'm only going to use magnitudes here, I'm not going to worry about positive or negative. We realize that this is going to be negative because we have we're below the x-axis, right? So the length of this side is going to be k times x, right? Because that's where this 2.5 newtons came from. I took my k and I multiplied it by my full x, which is 2.5 newtons. So erasing this just so that I don't overlap. This side here looks like k times x is 2.5 newtons. That's the length of that side. And the length of this side is, of course, x. And I'm going to write max on here is 5 newtons. And we use x max because our value here, this line here, is k times 5 meters, which is x max. And of course, this line here is x max. That is where our object ended, and that defines the boundaries of our rectangle. Okay, so our area here looks like a half, because I'm only taking half of the full area of the spring constant times x max times x max again. K times x max for this side multiplied by x max again. So my work, which is the same as my area, looks like 1/2 k times x max squared. And normally we drop this max subscript and just realize that the x is the position of the object at any moment, right? So I could stretch the spring an extra meter, and then I would have a different x max, and instead of writing it as x max, we write it as the position of the spring, which is just x. So the work done by a spring, and of course the work is the negative of the area, here is 1/2 k x max squared, because our area is below the x-axis. So that looks like negative 1/2 kx squared. So this is the work done by either compressing or stretching a spring. Now, a few notes on this. One is that the minus sign here indicates, if we just think back to our initial work discussion, we get negative work when the force of the spring acts against the direction of motion. Here, our force is acting against the direction of motion, leading to negative work. And this happens if I compress the spring as well. That is, if I compress the spring, my x vector points to the left, and my force vector points to the right. My force vector again points against the direction of motion, leading to a negative work. So, if you compress a spring, the spring does negative work. If you stretch a spring, the spring does negative work. As long as the spring is starting at equilibrium and being compressed or stretched, it is doing negative work. We just found that the work done by a spring as it is compressed or stretched is equal to 1/2 kx squared, where x is the amount that the spring is compressed or stretched. So this work is always negative as it is compressed or stretched, because as I pull the spring, its displacement vector points away from equilibrium and the force always points back toward equilibrium. Now, we can think about this process in reverse. So I can think about stretching the spring, having the spring do some amount of work, and then if I release the spring, all of that work is done back, is kind of given back by the spring, right? So I am giving, the spring is doing negative work as I extend it, and it's doing positive work as it collapses back in on itself, right? And this is exactly the same as our potential energy due to gravity. That is, if I lift an object, gravity is doing negative work, right? Gravity, the force of gravity points down while the displacement vector points up. So gravity is doing negative work as I lift an object. And then when I release it, it does positive work to give me that energy back, right? So just like I can store energy in lifting an object, I can store energy in stretching or compressing a spring. And I can get that energy back just by releasing the spring, right? And so just like with gravity, where we said the amount of work that gravity does, the negative really of the amount of work that gravity does, is the potential energy of gravity. The potential energy of a spring is the negative of the work done by the spring as it is compressed or stretched, which means that the potential energy of a spring is 1/2 kx squared, where again, x is the amount that the spring is compressed or stretched. Notice that this potential energy due to the spring is always a positive value. K is always positive, x squared is always positive, right? So if I stretch the spring, it's storing positive potential energy that I can get back, right? I release the spring and it goes shooting back to where it came from. I don't have a compressible spring, but you can imagine if I compressed a spring and then I released it, I would get that energy back as well, right? So either compressing or stretching stores potential energy in your spring. Okay, let's see an example of how this works and what kind of problem we would be able to solve using this. So let's imagine, I'll write it up here. Let's imagine that we have a spring attached to a mass, which is initially compressed a distance of 0.5 meters. And let's imagine that this spring has a spring constant of 2 newtons per meter. We can calculate the potential energy stored in this compressed spring, and I'll call this my initial state. So the initial potential energy of this system is only the energy stored in the spring. Looks like 1/2 times 2 newtons per meter multiplied by 0.5 meters squared. That looks like 1, that looks like 0.25, so that is 0.25 joules of potential energy stored in the spring here, right? I just use this formula. Now, imagine that I have a switch I can flip and it releases the spring, right? And shoots the mass out across the surface here. So I could ask, well, what is the energy of the mass right as it reaches equilibrium? Well, in that case, I can draw my final position here. And I could say, well, when the mass is here, I'll call this my final. So my potential energy final looks like 1/2 k times 0 squared. Because x is always measured as a distance from the equilibrium position, and my distance from equilibrium is 0 right now. So I have no potential energy of my system. And I want to use the work energy theorem, which says that the final energy of my system equals the initial energy of my system plus any work done by non-conservative forces. Now, remember that our definition of conservative forces are forces that give us all of their energy back. So any work that is put in, any work that I did in compressing the spring is given back in terms of kinetic energy. Any work that I did in lifting the pen is given back in terms of kinetic energy. So any energy stored in the spring is always returned, which means that it is a conservative force. So the spring force is conservative. It gives any energy back that it is storing. So my work non-conservative here is 0 because I had no forces outside of the spring force. If I, for example, had friction or air resistance or some other object pushing or pulling on it, then I could think about non-conservative forces, right? All of those are non-conservative. Remember, our only two conservative forces, things that count as potential energies that we use, are springs, which we just learned, and the gravitational force. So those two forces count as energy that we keep in our energy initial and energy final equations. Our work non-conservative, our forces due to our work done by other forces, is separated out here. But in this case, that is 0. So our energy final, which must only be in the form of kinetic energy because my box is clearly moving to the right. So is my kinetic energy final equals my energy initial, which is my potential energy initial. So all of the energy that was stored in my spring is now being converted into energy that is stored as kinetic energy or active energy in the object's motion. So I can say that my kinetic energy final equals my potential energy initial, which is 0.25 joules. And if I gave you a mass for the object, you could use that this is equal to 1/2 mv final squared. If I gave you a mass, you could solve for the final velocity of the object.